Okay, so last time we were talking about operators and eigenvalues and degeneracies. And so today, let's start by supposing that we have a Hermitian operator, which we'll call A. And that we know its eigenvalues. Last time we did some example, or at least one example of solving for the eigenvalues. So it's some set of numbers alpha, which could be, which are real, with degeneracy that I'm going to call G sub alpha. That means for each number alpha, the number of times it appears in the list is G sub alpha. Okay, and so the eigenvectors are going to be named after their eigenvalues for A. So I'm going to call them alpha, but then I need another label, rho sub alpha, to tell which one is which among the degenerate subspaces. So rho sub alpha is a number that goes from 1 up to G sub alpha for each alpha. Different eigenvalues can have different degeneracies. So those might well be different numbers. Okay, and these are going to be chosen to be an orthobasis. Okay, and the reason we know that's possible, at least if n is finite, is because we had theorem that in the notes is called 2.6.5. I'm not giving them numbers in lectures. So that theorem guaranteed that they could be chosen to form an orthobasis if the dimension is finite of the Hilbert space. Okay, and so what does that mean? That means that if we take the inner product, alpha rho alpha, with some other state, alpha prime rho alpha prime, that's one if and only if the states are the same. So that's Kronecker delta delta alpha alpha prime, but we also need Kronecker delta rho sub alpha prime. Okay, so those are an orthobasis if n is finite. And so now comes a definition. So the definition is that we're going to call this thing an observable if two things are true. The first thing is that it's Hermitian, as we've been assuming above. And the second thing is that this orthobasis is a complete one. Okay, so the alpha rho sub alpha are a complete orthobasis, which means that they satisfy the following equation, that the identity operator is equal to what you get when you sum over all these states, alpha, and then for each alpha, you have to sum over rho sub alpha from 1 up to the degeneracy G sub alpha of alpha rho sub alpha ket alpha rho sub alpha bra. Okay, and this is the completeness relation. And as I think I mentioned last time, it's almost a tautology that whenever you're stuck on something and you don't know what else to do, a good thing to try is the completeness relation. It works amazingly often that that's the solution to whatever problem you have. Okay, now, if the Hilbert space is finite dimensional, that's actually redundant. Part B is redundant with part A because we had this theorem, but the theorem assumed that it was a finite dimensional Hilbert space. So part B is redundant. if, oops, I didn't leave much space there, if n equals finite. But the reason it's there in the definition is to avoid pathological cases where you could have infinite dimensional Hilbert spaces and you won't have a completeness relation. And we'll see later why you cannot call the thing an observable unless it obeys this completeness. Okay, so what if these eigenvalues alpha are actually continuous, which happens quite a bit if you have an infinite dimensional Hilbert space. So this would include the case of uncountably infinite Hilbert space. Then what we're going to do instead is we're going to say the inner product of a state with another one that are both eigenstates of our observable A is instead going to be the Dirac delta function instead of the Kronecker delta. Delta alpha minus alpha prime, delta rho sub alpha prime. Okay, so this is the Dirac delta function, which you've hopefully seen before. We will talk about it later in the lecture. If you haven't, we'll introduce it formally. Okay, and then instead of the sum over alpha in the completeness relation, the completeness relation looks like this. Instead of summing, you just integrate. You integrate over alpha. We have a sum rho sub alpha of alpha rho sub alpha bra ket alpha rho sub alpha bra. Okay, so this is also the completeness relation. Completeness. And there are even situations where the rho sub alpha are also continuous. So then what you do is you just replace the sum over rho sub alpha by an integral over rho sub alpha. Okay, so that's our definition of what an observable is. And now we're going to write down a theorem. Although the theorem will only prove in the case of a finite dimensional space. So the theorem says if I have two observables, let's call them A and B, and they happen to commute. So A commutator B is 0. Then there exists an orthobasis in which they're both diagonal. So one way of thinking about what that means is if you form the matrix representation of both of these operators in that orthobasis, then, which is just the set of matrix elements arranged in square arrays, then they'll both be diagonal. Okay, and so here's the proof. And this proof is really only valid, but it's true anyway for any space, but this is true for n finite, the dimension of the Hilbert space. Okay, so the proof is, first, we know that we can, from what we just defined, we know that we can find a set of states that are an eigenstate, that are eigenstates of A. Okay, and so we know we can find a set of states such that A acting on, I'll give them an index now, n, alpha n and rho sub alpha n, are equal to the eigenvalues, alpha n times the eigenstates back again, or the eigenkets back again. Okay, that's just the definition of what it means to be an eigenket with eigenvalue alpha sub n. Okay, and now since we're assuming that they commute, then it's true that if we form these matrix elements, alpha n, rho alpha n, with the operator b, now I'm going to put alpha n prime, rho alpha n prime, that's equal to 0 when n and n prime are different. Okay, and the reason we know that is another one of the theorems that we proved, which was theorem 2.6.3 in the notes. Okay. So what does that mean about the matrix representation of B? It means that we can write B in matrix form in the following way. Okay, there's a block here that I'm going to call B sub 1, another block B sub 2, another block B sub 3, all on the diagonal part of this thing until we get to B sub n. Okay, and so I'm dividing this matrix up into blocks. And so the non-zero entries are just the ones that I'm shading here. Okay, so they're shaded blocks. These are the subspaces with the same alpha n eigenvalues. Excuse me. Okay, so those are the dimension of those blocks is each one has dimension g alpha n. So they're square submatrices g alpha n by g alpha n. Which we're calling B sub n. And of course, some of them may not be degenerate. If so, if g alpha n is equal to 1, then that's just a 1 by 1 matrix. But in general, they can have larger dimension on the diagonal. So when g sub alpha n is not equal to 1, what does the block matrix look like? Okay, so to understand that, we can look at the matrix elements, alpha n, rho alpha n, b, alpha n, rho alpha n prime. Okay, so this is a matrix element that has the same eigenvalue for alpha, but different degeneracy labels. That's why the rho prime has a prime on it. Okay, for rho alpha n and rho alpha n prime equals 1 up to g sub alpha n. Okay, and one thing we know about this matrix, this set of matrix elements, is that because B is Hermitian, these are Hermitian matrices. Okay, that's the key to the whole thing. That means we can diagonalize them. We had another theorem to that effect. Okay, and so we can choose some basis in which they're diagonal. And that basically is the proof of the theorem. So just to summarize, the new basis has a representation for A because we already chose it to be diagonal in that basis. That is just alpha 1. There's a bunch of alpha 1s, however many the degeneracy is. And then there's alpha 2s. Okay, and so on along the diagonal. They're all diagonal. And for the matrix B, its representation, that's the double arrow notation, that means the representation of the operator in a given basis. And so that's going to look like beta, that's the eigenvalue of B with a label alpha 1 telling you that it's in the subspace of alpha 1. And this is the first one. And then there's beta alpha 1, 2, up to beta alpha 1, G alpha 1, because there are G alpha 1 different betas in that subspace. Okay, and so that's the first block. And then the second block is going to be beta alpha 2, 1, beta alpha 2, 2, up to beta alpha 2, G alpha 2. And it just keeps going like that along the diagonal. Okay, and so they're both diagonal in this basis. Okay, so I want to emphasize the key thing was that within each subspace, we had this matrix that's Hermitian, and therefore we're guaranteed to be able to diagonalize it. And when we diagonalize it, we're diagonalizing it within each block, so it doesn't change the other blocks. So in other words, what's going on is the unitary matrix that we use to diagonalize this thing is one outside of each block. It only acts separately within each block, and that's what guarantees that we can put it in this form for both A and B. Okay, so the eigenstates can be labeled now by alpha and beta, but then there might still be other information needed to distinguish them. So I'm writing dot, dot, dot here for other labels for any remaining degeneracies, which can occur. So what does that mean? That means the A, if I look at this block right here, the A operator has all the same eigenvalues within that block. So A doesn't distinguish different vectors that are eigenvectors within that block. B could have different eigenvalues within that block, so that could help distinguish them, but nothing in the theorem guarantees that these betas here will all be different. So it could be that these are still degenerate. And so the moral of the story there is that to tell them apart, to tell apart the degeneracy, the degenerate states, or the remaining degeneracies, if there are any, you may need further observables. Okay, so one way to think about this is if you have different states that are really physically distinct, that means there's some physical difference between them, then there ought to be some way of choosing the observables to tell them apart. And if you can't tell them apart, that means you haven't found all the relevant observables yet. And so you need to look for more. And when you're done, if you've succeeded in finding a set of observables that tells apart every possible state, then that's called a complete set of commuting observables. And so we're going to call that a CSCO, complete set of commuting observables. And so what it is you assume it's some set of observables that we can call A, B, and C, up to however many there are. And this is, in every case that we will ever deal with, this is going to be finite. It doesn't go on forever. There's a finite number of these. And it's usually a small number, like 2, 3, or 4, even if you're talking about an infinite dimensional Hilbert space. But anyway, they're chosen so that A acting on eigenkets alpha, beta, gamma. These states are named so that they have A eigenvalue alpha, and they have B eigenvalue beta. And C eigenvalue gamma. And you just keep going like that for however many there are. But again, it's usually, in every case we will deal with, it's a finite number. And here's the key thing, is that if you've chosen these eigenkets, they have to be unique. So where each alpha, beta, gamma ket is unique. That means if you choose the eigenvalues alpha, beta, gamma, there's only one ket with that set of eigenvalues. Okay, and so then this complete set of commuting observables, A, B, C, however many there are all diagonal in this basis. So a lot of times in a quantum mechanics problem, that's what you want to do. That's part of the important process of solving a problem, is to find the complete set of commuting observables. The reason is because diagonal matrices are very, very easy to work with. And so whatever question you might have to ask about a system, it's going to be much easier if you first get the complete set of commuting observables and then proceed with the rest of the problem. Okay. Questions on that? No?
Actually, I just wanted to ask a quick kind of just semantics. Well, not semantics, but just a quick question. Is this still part of the proof, or is this something different?
No, so the proof, and it's sort of a physicist proof, not a math proof, sort of ended here, right? It was just the observation that we could write A and B both diagonal.
Okay, so this is building on something new now.
Yeah, so CSCO here is really a definition. It's saying, okay, I can have A and B both diagonal, but I can also have a larger number, A, B, C, etc., all diagonal. And basically, you keep adding observables to your list of commuting observables until you can't add any more, or until you don't need any more, I should say, to distinguish your eigenkets.
Okay.
Good.
Yeah, thanks.
Other questions? Okay, so let's go and talk more about the case of an uncountably infinite Hilbert space, infinite dimensional state space. Okay, and the quintessential example of this is one position operator. So we're going to start with an observable that we're going to call X. Again, in this class, I always use capital letters for operators that are observables, or more generally just for operators. This could be, the position of a particle in one dimension, but it doesn't have to be. It could also be the angular position, as we'll talk about in a little bit. Okay, and now we can ask, what are its eigenvectors? And since we don't know, let's say we'll just name them. That x acting on an eigenvector, that's a lowercase x, is the number x times the ket x back again. So physically what this means is if your state of your system is x, the ket, then its position is known to be the number x. Okay, and so the position of a particle can take on an uncountably infinite number of values. Continuous, uncountable, meaning they can't be put in one-to-one correspondence with the rational numbers or the integers, infinity of values. And so one example of this is it could be that the allowed values are just from minus infinity to infinity, with 0 somewhere in the middle. And so all of those values are allowed. But it's also possible that maybe only values between two numbers a and b are allowed. Okay, so I'm just going to shade this out to say those aren't allowed and those aren't allowed. Okay, and these are allowed values for x. Okay, so we have these kets, and now what we'd like to do is define an inner product among the kets. So let's just do that. Define an inner product. How should we do that? We should, first of all, choose them to be orthogonal. So the inner product of x and a different x called x prime is going to be 0 if x is not equal to x prime. Okay, and what if they are the same? Then it's tempting to say that the inner product of x with itself should be 1, but I'm going to put a question mark above that because it turns out it's impossible. It does not work. Even though that's what we would like to do based on everything we've seen before. That would be standard orthonormality. So let's prove that it doesn't work. Okay, so to see why it won't work, let's start with the completeness relation. Because the completeness relation is usually the guide to all wisdom. Okay, and so because this thing is a continuous value, instead of summing, we have to integrate. So we're going to do an integral from a to b. A could be negative infinity, b could be positive infinity, but we're going to integrate dx prime of the ket x prime multiplied by x prime Lebras. So completeness says that should be the identity operator. Okay, and we had to replace the sum by an integral. Because it's a continuous value, and there's no way to sum over something that's continuous as if it were discrete. Okay, so now these are just the eigenkets of x. Now let's consider some arbitrary ket that's not necessarily an eigenket of x. So I'm going to call this arbitrary ket, let's call it f. Okay, so it's not an eigenvector or an eigenket of x, or not necessarily at least. And now let's consider the inner product of x with f. So what is that thing? It's clearly dependent on x. So it's a function of x. And so we can write it this way, f of x. That's just sort of the definition of what the function is that gives us this inner product. And this is otherwise known as the position space wave function. That's the definition of what a wave function is. Okay, and now we're going to plug in completeness. So we can write this as integral from a to b dx prime, x prime, x prime f. This is f of x prime, the way we defined it. And this x with x prime is 0 unless x equals x prime. Okay, so if it's 0 for x equals x prime, that means we didn't really have to integrate over from a to b. Instead, we could write this. We could write f of x is equal to just a little bit below x and a little bit above x. So from x minus epsilon up to x plus epsilon dx prime, f of x prime. And then this x prime thing has to go in there. Okay, so again, the reason is because it was a waste of time integrating over most of these x primes, because they just don't contribute, because this was 0. And so we can just integrate from just below x prime, just below x to just above x. Okay, and then that is actually going to be what we're going to call our delta function. In fact, that's sort of our definition of the delta function. Okay, and so it must be true that delta of x and x prime is equal to 0 if x does not equal x prime, and it's infinity if x equals x prime. Because as epsilon shrinks to 0, the only way you can get a finite answer by integrating over an infinitesimal integral is if the thing you're multiplying by is infinity, in such a way that the integral from x minus epsilon to x plus epsilon of delta of x prime dx prime is equal to 1. Okay, and so this is the Dirac delta function. Okay, and it's the way I've written it, it's a function of x and x prime, but it's actually only a function of x minus x prime. It only depends on their difference. And you can think of this as the limit of some very narrow, very peaked functions.
Professor, I'm slightly confused. Maybe I'm being impatient, getting ahead of myself, but if that integral is 1, then why do we say that the thing we were showing doesn't work earlier doesn't work, if that makes sense?
So the problem is that when x equals x prime, it had to be infinite. That's the problem.
Okay.
So it's not
Gotcha.
1, it's infinity.
Gotcha. Okay.
Okay.
All right. Thank you.
Sure. So we think of this Dirac delta function as the limit of very narrow, sharply peaked functions. Now, that limit in a mathematical sense doesn't actually exist, but we're going to pretend it does because this is not a math class. So we're going to just think of it heuristically in the following way. I'm going to draw a sort of a pseudo graph as a function of x prime of what delta of x minus x prime is. Okay, and so here's the value x. And so what this thing looks like is it's 0 everywhere except near x equals x prime. And there it has this very sharp peak. Okay, and the height of the peak is, let's call it L. And the width of the peak is 1 over L. Okay, and that's how it can be, the area under that is L times 1 over L, which is 1. Okay, and so that's how it arises that the integral of it is 1. But now we're going to take L goes to infinity, and so the value of the function at that point is infinite. Okay, so it's the limit of this thing as L goes to infinity. So that's one way of thinking about what the Dirac delta function is. Again, this limit doesn't actually exist as a real mathematically rigorous limit, but you could define it that, you can think of it that way. Another way that you could sort of think of the Dirac delta function is you can think of it as the limit of a very sharply peaked Gaussian. So here's the point x again, but this time I'm going to graph it as a Gaussian bell curve. Pretend that's a Gaussian. Okay, and so now this is the limit as some number I'm going to call delta goes to 0 of 1 over the square root of pi delta squared exponential of minus x prime squared over delta squared. There's lots of different ways to write it. I think I may have chosen a different way in the notes. I actually don't remember at the moment. Okay, but if you integrate this Gaussian function, you get 1, no matter what delta is. But the smaller you take delta, the sharper and sharper peaked it gets. So that would be one value of delta. Another one might look like this, super sharply peaked about that point. Okay, so some things to note about it is delta of x prime equals delta of x minus x prime equals delta of x prime minus x. So it's an even function. And so we can summarize in terms of the kets that were eigenkets of position that x prime, the matrix element, is the Dirac delta function, this thing that's infinitely large but infinitely narrowly peaked for continuous x, which is not the Kronecker delta. And then the way the orthonormality works, orthonormality, is this. This is the orthonormality of our basis x. And the completeness relation, and this is similar to what we've already written down, is I integrate over all x that are allowed, which is from a to b, of dx prime, x prime, x prime. That's the identity. Okay, and so this integral, the sum, the usual sum is replaced by this integral. Okay, and so these are sort of the defining orthonormality and completeness relations for our position eigenstates. But here's where I have to tell you that this is all sort of a lie, but it's morally okay. So technical aside, the kets that we've been talking about as eigenkets of position cannot have finite norm. So before, when we've been talking about kets, we've been talking about the fact that, oh, if the norm isn't 1, then you can just multiply by 1 over the square root of the norm, and then it will have norm 1. But you can't do that here because this thing is either 0 or infinity. And if it's infinity, then when x equals x prime, you can't take 1 over the square root of infinity. It just doesn't work. So these things cannot have finite norm. And so we give up on that and we just declare them to have infinite norm and use them anyway. But what that means is because delta of 0 is infinity, these are not physical states. Okay, eigenstates of position, perfect eigenstates of position are not physical states, and they're not even part of the Hilbert space because they don't have finite norm. Okay, instead, these kets are idealizations of states with perfectly known position. They don't actually exist physically, but we use them anyway because they're so useful. So they're idealizations with perfectly known position. But because they're not proper kets, they're not a basis either. So the set of all x is technically not a basis. I think somebody earlier in the course had asked about this, and I alluded to this fact before, that although we often pretend otherwise, these are not physical states, they're not part of the Hilbert space, they don't form a basis, but we're going to use them anyway because they satisfy all the other properties. That we would want. Okay, they satisfy Dirac orthonormality, which is you replace the Kronecker delta by the Dirac delta function here. Okay, and completeness. And so even though proper mathematicians would feel free to shake their heads sadly at the fact that we're cheating, this is so useful from a physical point of view that that's what we're going to do. Okay, so without apology, from now on, we're going to treat them as if they were physical. And we're going to treat the set of all x kets as if they formed an orthobasis. Even though, technically, from a purely mathematical point of view, it's just not true. Okay? So if things like that bother you, if you're very mathematically minded, I guess that's too bad. That's just the way we deal with it. Okay, so let me again summarize some of the properties of the Dirac delta function in a slightly different way. And because the delta function is technically not a function, you can take this as its definition, what I'm about to write down. Okay, so one way of defining what the Dirac delta function is, it's the object such that the following is true. That if I integrate from, let's say, b to c dx of any function f of x. Now, a mathematician would say f of x actually has to be somewhat smoothish, continuous, or something like that. I don't really care about the technical details, but multiplied by the Dirac delta function, then I get one of three possible things. I get the value of f at a, where the delta function has its 0. That's if b is less than a is less than c. But it could be that I hand you an integral like that with b is larger than c and a is in the middle, and then I would get minus f of a. So that's if c is less than a is less than b, and it's 0 otherwise. So that would include all cases where a is not between b and c. So the way we think about this visually is, here's the x-axis, here's my graph of f of x that I'm going to draw, some function. And now I'm going to draw my cartoon version of the Dirac delta. Oops, that's not what I meant. Of the Dirac delta function. Okay, which was this sharply peaked thing here. Okay, and then here was, let's say, the point B. Here's the point C. This value where the Dirac delta function has its peak is A. And so what this thing is saying is doing integrals involving the Dirac delta function is super easy. All it does is it picks out the value of the function you're multiplying by at the place where the Dirac delta function's argument is 0. So again, delta of x minus a is 0 if x is not equal to a, and it's infinity if x does equal a. Okay, another way you can write it is that delta x minus a is the derivative of the Heaviside step function. Okay, that's what this theta is. And so to graph what it looks like, the step function at a point A is just, the thing that's 0 until you get to where A is, and then it jumps up to 1. Okay. All right, so let's do one more thing with this before we quit for the day, and that's relate this to Fourier transforms. So recall a Fourier transform of a function. Let's call it f of x. So if you're given f of x, then the Fourier transform f of k is defined to be 1 over the square root of 2 pi, integral from minus infinity to infinity of e to the minus I k x prime, f of x prime, dx prime. And then you get back the function f from the Fourier transform by doing a similar looking integral, but e to the I kx in this integral, and then the Fourier transform function f of k. And you're integrating with respect to k. Okay, so now let's plug in one into the other. Oops. Okay, and so we can write f of x equals, I'm going to plug my f of k in the first line into f of k in the second line. And so I get two factors of 1 over the square root of 2 pi. So that's 1 over 2 pi. Integral minus infinity to infinity dk, e to the I kx. And then another integral minus infinity to infinity dx prime. That's from here, of e to the minus I k x prime, f of x prime. And now what I'm going to do is I'm going to rearrange the order of integrals. So I'm going to leave the x prime integral on the outside. And move out the function f of x prime there too. Then I'm going to write my factor of 1 over 2 pi. And then I'm going to write integral minus infinity to infinity of e to the I k x minus x prime dk. And let me put parentheses around that part of it, because if you stare at this and you go back to when we first wrote down what the delta function was, that means this thing right here has to be the Dirac delta function. Okay, so just to summarize, let's call x prime a, just for variety. And so what we've proved is that the Dirac delta function of x minus a, I can write as 1 over 2 pi integral minus infinity to infinity e to the I k x minus a dk. Okay, so this is yet another way, useful way of writing the Dirac delta function. I'm writing it as a integral over another variable k, which is, it turns out, going to be related to the momentum in the momentum of a particle when we're talking about particle states. Okay, so that's it for today. Are there any questions before we get to? Oh, we'll answer homework questions later, but are there any questions on the lecture before we stop?
I have some questions from the notes.
Okay. So maybe the thing to do is if they're not directly related to the lecture, I'll stop recording here. And then people who want to leave can leave. And if people have other questions, whether they're on the notes or the homework, we'll stick around and answer them until they're done. Okay, so I'm going to stop recording.